This is very important lemma. If f is bounded and measurable on closed interval ab and capital Fx is equal to the integration from a to x ft dt plus f of a, then f dash x is equal to fx for almost all x in closed interval ab. So for this, first we need to show that this capital F is of bounded variation on closed interval ab, and then fn x tends to f dash x almost everywhere, and then the integration from a to c on f dash x on this is equal to the integration from a to c fx dx, and at last from this step we get that f dash x is equal to fx almost everywhere. So we need to first show that f is of bounded variation. So for this, let's take the subdivision of closed interval ab. This is less than x2 up to xk, that is equal to b. So this be any subdivision of closed interval ab, right? Then we know that small t is equal to the summation I going from 1 to k, the absolute value of capital Fxi minus f of xi minus 1. So this is further equal to the summation I going from 1 to k, the mod of what is given to us, that capital Fx is equal to the integration from a to x small ft dt plus capital Fa. The capital F of x is equal to the integration from a to x ft dt plus capital Fa. So let's apply this. So this is the integration from a to xi ft dt plus f of a, right? Minus, for this the integration is from a to xi minus 1 on ft dt plus fa mod. Because there is a negative sign, so these two cancelled out, and this is equal to the summation I going from 1 to k, the mod of the integration from a to xi ft dt minus the integration from a to xi minus 1 ft dt. Because I need this sign to be positive, for that we have to interchange the limits. So the sign changes when we interchange the limit. So here I am having xi minus 1, here a. Let me write this integral first over here, right? And now let's merge these two integrals. So this integration is from xi minus 1 to xi ft dt. And because it is your mod, so this is less than equal to the summation I going from 1 to k, the integration on the modulus of ft, and here it is dt, right? And when we take the summation on this integration, so when adding all these integrals, we get the complete integral from a to b ft dt. So we get t to be less than equal to the integration from a to b mod of ft dt. This equal to sign is the value for this integral when summing up the integrals along with this inequality, right? The left hand side we have this t. So we are getting t to be less than equal to this integral. And now taking the supremum over all the possible subdivisions of closed interval ab. So we get, when taking the supremum, this t will be changed into the capital T. And the supremum is over all the possible subdivisions of closed interval ab. So from a to b, right? So this total variation is less than equal to the integration from a to b mod of ft dt. And because it is given that this f is bounded, right? So because f is bounded, so this integration is finite. And when this total variation is finite, we say that capital F is of bounded variation. For bounded variation, the total variation should be finite. So therefore, f is of bounded variation on closed interval AB. So we have shown the first result. So we have shown this first step. The next step we have to show that fnx is tending to f dash x almost everywhere, right? So for that we need to consider what is this fnx. Now as we have shown that f is of bounded variation, which means f dash x exists, yes, its derivative exists almost all x in closed interval AB. So thus we have to write that f dash x exists for almost all x belonging to the closed interval AB. Now moving on to the second step, it is given that since f is bounded, it is given that small f is bounded on closed interval AB, right? So therefore now using the definition of boundedness, mod of fx is less than equal to capital K, let's say, for all x belonging to the closed interval AB. This is for some real k, for some real number k. Let's define f and x to be equal to f of x plus h minus f of x divided by h, with h to be equal to 1 by n. Then this f and x will be equal to 1 by h into, how to write f of x plus h? It is given that f of x is equal to this right hand side. We are going to use this definition now. It is the integration from a to x ft dt plus capital Fa. The limits are from a to whatever on capital F is depending. Here f is depending upon the sum of x and h. So we write the integration from a to x plus h ft dt plus f of a minus writing the value for fx. So it is the integration from a to x ft dt plus capital F of a. Because of this negative sign, again I am cancelling these two, and we get 1 by h into the integration from a to x plus h ft dt minus the integration from a to x ft dt. I would like to interchange the limits so that I can get positive sign over here. And now when I merge these two integrals, and now writing this integral to this side first, and now merging these two integrals together, we get the complete integral from x to x plus h ft dt. On the left hand side we have f and x. And now when taking the mod on this, the mod of f and x, this is equal to the mod of 1 by h, the integration on ft dt, on ft dt. So this is further less than equal to 1 by h, the integration from x to x plus h, the mod of ft, and then dt. Because f is bounded, we have written mod of fx to be less than equal to k for all x belonging to this closed interval AB. So if I take that x to be equal to t, then we get this mod of ft will be less than equal to k. This is less than equal to 1 by h, the integration from x to x plus h, mod of ft is less than equal to k, and there dt. So this is equal to 1 by h. Solving the integral, k is a constant taking outside of this integration. Integration for 1 is t, and the limits from x to x plus h. So this is equal to k divided by h. When putting the upper limit we get x plus h, minus putting the lower limit we get x. So this h is cancelled out with this h now. So we have k over here. So thus we get that what is on the left hand side? It is mod of fnx. So the mod of fnx is less than equal to k for all x belonging to the closed interval ab, right? Now since if I take limit n tends to infinity on fnx, if I take limit n tends to infinity on fnx, that will be equal to limit h tends to 0 on f of x plus h minus f of x divided by h. And this is nothing but the definition of the derivative f dash x, right? So we have shown that because this mod of fnx is less than equal to k, it is bounded, and limit n tends to infinity on fnx is f dash x. So therefore fnx is tending to f dash x almost everywhere, right? So from these two results we can now use the bounded convergence theorem on this. These two results are required by the bounded convergence theorem. And whenever these two results we have, we can say from bounded convergence theorem that the integration on this is equal to the limit n tends to infinity on the integration of this. This is what we are now going to use in the next step. So after showing this second step, we will get this third step by the use of bounded convergence theorem. So now we have to apply the bounded convergence theorem in the second step, taking the integration on this capital F dash x from a to c dx, and this is equal to the limit n tends to infinity on the integration on this from a to c. And we have defined this fnx to be equal to limit n tends to infinity on fnx is equal to limit h tends to 0 on fx plus h minus fx divided by h, writing this in terms of h. So this is equal to limit h tending to 0 1 divided by h in the integration from a to c f of x plus h minus f of x and is dx. Taking this integral inside, so this is limit h tends to 0 1 divided by h, the integration from a to c on f of x plus h minus the integration from a to c f of x dx. So this is equal to limit h tends to 0 1 divided by h. How can we write this first integral as further? F is depending upon x plus h. So this integral can also be written as for the limits a plus h to c plus h, and here we write f of x dx, minus writing the second integral as it is. And now using the additive property for the integrals, this further can be divided as from a plus h to a, this integration, plus then from a to c, plus from c to c plus h. This is the property I have used over here, and then minus the second integral as it is. So these two cancelled out. In the next step, I would like to interchange the limits of this integral. For that, we write this integral as from a to a plus h f of x dx, but with negative sign. So this integral is equal to this. So let's use this in the next step. So this is equal to the limit h tending to 0 1 divided by h. I'm writing this integral first, c to c plus h f of x dx minus the integration from a to a plus h f of x dx. Multiplying this 1 by h inside. Now if I take a real number between c and c plus h as t, and a real number between a and a plus h as s, and also f is continuous, then by mean value theorem this first integral will be changed into limit h tends to 0 f of t into 1 by h, the integration from c to c plus h dx, minus the second integral will be changed into f of s into 1 by h, the integration from c to c plus h dx. So this will be further equal to limit h tending to 0. This integration will gives us the value. The integration for 1 with respect to x is x, and the limits from c to c plus h, that gives h. So this h will be cancelled out with the h in the denominator. Similarly, when integrating this, again we get h. That will be cancelled out with the h present in the denominator. So after integration we get the result to be, this is f of t minus f of s. Reason: using the mean value theorem for this step. And by the definition of continuity, limit h tends to 0 on f of t becomes, because t is lying between c and c plus h, so this becomes f of c. And when applying the limit on f of s, because s lying between a and a plus h, so this will be minus f of a. So what is on the left hand side? On the left hand side we have a to c integration f dash x. So we have got the integration from a to c on f dash x dx, that is equal to f of c minus f of a. Right? This is further equal to, applying the definition of fc, it is the integration from a to, because f is depending upon c, so this is from a to c, f of t dt plus f of a. It is given in the very start of the lemma. This is given to us, right? And then minus fa. So these two cancelled out. And we get the integration from a to c f dash x dx to be equal to integration from a to c f of t dt. We can also interchange this t with x for x belonging to the closed interval ab. So writing this for the variable x. So this further implies the integration from a to c. If I take this integral to the left hand side, this is f dash x minus f of x dx to be equal to 0. And when the integration of this integrand is equal to 0, that implies what? For all c belonging to the closed interval ab, this implies what? This implies f dash x is equal to fx. When the value of the integration is 0, then the integrand itself is 0, so that implies f dash x is equal to f of x. Almost everywhere this is what is required to be proved, right? So we have proved this result. This is a very important lemma. All right, thank you, have a nice day.